universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to Sky Tour Radio. This is Mark D'Antonio here at KGRAradio.com. I'm your host of Sky Tour Radio, here with Amanda, and tonight we have Daryl. This is a special episode, and this episode grows out of a conversation we had earlier where we discussed the new Event Horizon Telescope imagery that we saw and commented on earlier today. It is a wonderful 2-hour conversation between the three of us, and we had a chat room full of people that were listening as we were presenting to them as well. So give it a listen and enjoy here on KGRAradio.com.
Hi, everybody. Hello, Mark. Amanda, you don't have to call me Daryl M. I think everybody knows my name by now.
Yeah, don't Mason. Oh, I said it.
Daryl Mason.
Yeah, I know.
You're a fixture on Sky Tour Radio now, Daryl, like it or not, right?
Yeah, I guess so, Mark. Hi, Mark. How are you?
I'm okay. I got my system back up now, so I'm using that, and it hasn't
sound
days,
a lot better.
Yeah, I know, and it's much better than the cell phone. But so anyway, you were saying Daryl was going to let you because they were saying she was asking what your impressions were of the discovery, and I have mine. You have yours, I'm sure.
And I want to hear both. So,
right.
whoever would like to start?
Jump in, Mark.
Oh, all right. Well, first of all, it is what I expected to see. Here's why. Because it was using sub-millimeter telescopes. So in other words, it wasn't seeing the light that we see with our eyes. It was seeing light that's longer wavelength than our eyes see by far. So it's out in the radio spectrum. So the images captured by radio telescopes tend to be, in general, pixelated looking images to the general public who see them, but they don't look like photos from Pluto, like from Event Horizon, from the New Horizons spacecraft. Okay, the Event Horizon telescope takes images that are using radio wave data. So, and the dishes receive these signals and convert them into imagery. And so the problem is the size of the dish gives you a resolution for the object you're looking at. Just like the diameter of a telescope can give you the better resolution of an object you're looking at. So by combining all of these telescopes and then allowing multiple observations throughout the night and day, incidentally, since they, if it's up in the daytime for some of these locations, it doesn't matter because radio waves, you can still do radio observations during the daytime. I did. I did radio observations of Io's torus, that is an envelope basically of sodium ions that was surrounding it. And I did that with a telescope that we made, and that was used during the day because Jupiter was out during the day at that time. So you just have to be careful not to let the sun get near because the sun is a source of radio as well. So when you image in the radio spectrum, you see things differently. And so what I saw on the screen was basically a sum of all these many telescopes sweeping out observational data for the course of the time that they could, the Earth was rotating out from them. And they only do it to a certain height above the horizon, so it's a sort of a narrow band. It's not the entire rotation of the Earth. But in any case, what they did by summing this stuff together, they basically made the Earth like an 8,000 mile diameter telescope, a crude telescope in a sense, but a telescope nonetheless. And because it was that large, it gave us the ability to actually image a very tiny object. And when I heard it suggested it was like looking at a quarter. And what did he say from how far away? A quarter, like in Los Angeles, image from New York or something like that. Being able to see the quarter, that's the kind of resolution that we ended up getting here. So that is entirely dependent on the diameter of your telescope. And if the diameter of your telescope is the diameter of the Earth, well, that's great. Now, if they were to then take these observations throughout the year, as they have been actually, and then use the Earth's orbit, then we could have a telescope the diameter of the Earth's orbit, and that's something that may very well be in the works. The only problem is if the object sufficiently changes over the course of, say, 6 months from orbit, one side of the orbit to the other, then that could kind of make our image blurry, and not really give us an adequate look. So the reason they used Messier 87, one of Daryl's favorite objects, I believe.
Oh yeah.
Because we've imaged the jet and Sky Tour live stream quite a bit. We saw it just the other night, I believe.
Yep.
We've been seeing it quite often, actually. I remembered that one.
Yeah, that's right. And so when we actually look at M87, we're seeing it 55 million years ago. But it's also remains relatively unchanged, even though they can see changes week to week in the observations. Okay. And that has to do with, and of course, that has a final verdict on what the final image looks like as well. And then someone said, well, why don't we just image Sagittarius A, the black hole in the center of our galaxy? Well, that'd be wonderful. Now, we do have obscuring dust and so forth between us and the black hole, but radio waves might be able to make it through that, the submillimeter band maybe. The trouble is, though, that being that it's so close, relatively speaking, it does present issues for us. And so they'll have to be very careful about imaging Sagittarius A. But hey, it could ultimately end up being the most beautiful image of a black hole in history.
Can I jump in here?
Yes.
Well,
Okay. As Mark mentioned, it was the image was made by radio telescopes, okay, and it created a synthetic aperture. Mark mentioned that the bigger the scope, the higher the resolution, whether you're in visible wavelengths, radio, or whatever. They effectively created a telescope with an aperture of 8,000 miles. The image itself, I wasn't surprised by what I saw. I wouldn't say I was disappointed, but it looked pretty much like what I was expecting. And if you've seen the movie Interstellar or, recent movies, whatever, that purport to show black holes, well, it looked pretty much like that. It will be interesting to see if they get additional images down the road. I bet you they have an image of Sagittarius A star. They just didn't show it. It would be interesting to see our own, and we might see particular differences from one black hole to the other. But I bet you down the road they're all going to look like each other.
Yeah.
The M87 part, hey, I thought that was great. They went ahead and showed it. As mentioned, we have looked at M87 several times recently on Mark's Sky Tour live stream. And we talked about the jet. Well, that jet is coming from that black hole. And that we can see it at all, I think, is really something.
Yeah, that's one piece of the jet that's coming toward us, right? And the other is on the other side going out away from us. We can't see it.
Yeah, you might have noticed at one point during the presentation, they showed a Hubble image of that jet. I think I saw that at the Wikipedia article on M87. It's easy enough for you to find, and you'll get a good high-resolution visual image of the jet coming out of the big elliptical galaxy. For a sense of scale, that jet's like 260,000 light years long, if I remember correctly. And that's like 2.5 times the diameter of our entire galaxy. So it's huge. The whole interferometry thing is what it's called. They called it very long baseline interferometry, or VLBI, I guess. That's what happens when you can integrate 2 or more telescopes, whether it's optical or whether it's radio. They have to bring the data together so it's in phase, I guess you would say. Mark, I think that would be. term, wouldn't it? And that means they have to get the data down to the microsecond from one telescope to the next telescope so they can successfully integrate that data. Uh, that is, every telescope that was involved in the project, they have to nail the time down exactly to be able to integrate all that data, basically catching the same wavefront as they said during the presentation.
Yep, that's right.
I think it's great. I think the image looks like it reminded me, Mark mentioned this, looked like every other radio telescope image I've ever seen. It's kind of fuzzy, kind of pixelated, uh, but it gets to the point where it's not necessarily that they do it well, but that they can do it at all. I would be curious to see down the road, maybe as Mark mentioned, with the really very long baseline interferometry, whether it's space telescopes expanding the synthetic aperture, or sort of like when they do parallax on stars and such, that if we have a baseline, the diameter of Earth's orbit around the sun, that we might really get somewhere and be able to get some real high resolution images.
Oh yeah, definitely.
Okay, well when we first looked at it at the black hole, I think they called it an emissive ring.
Yes.
Was it? Okay, and it was light protons around the black hole.
Photons, yeah.
Photons, sorry.
Yeah, that's okay. And that light ring is a consequence of the photons that are very close to this gravity well, basically in the space-time fabric is what it's called, such that they are very close to not being able to ever escape orbiting the black hole without getting away from the black hole. And that what you were seeing is the photon ring. It's called the photon ring. It's an area above the black hole, above the event horizon, actually, where the photons are in a very, very close orbit to the event horizon. And the people will say, well, light has no mass. How come it's affected by gravity? Okay, the answer to that question is really a point of view. Think of it this way. Gravity warps space. Now, we could warp space. If we could warp, say you have a long, flat sheet that's stretched taut, and you put a heavy bowling ball in the center of it. Well, if you put another marble at one end and you let go of the marble, it's going to roll down toward that bowling ball. And if you give it just enough of a trajectory, it might do a little arc around the bowling ball and go the other way. Okay? To the marble, it's going straight. Okay? The marble's going straight at any 1 second. But to us observing it, it's making a curve because the sheet is curved. Space is the sheet. All right. So gravity will distort space. And thus light, which thinks it's going straight, is constrained to go through space, follow space normally. And when it follows space, that is to say the architecture of space as we've deduced it, then it can translate into a curve. And it can look like it's curving. So yes, it may be massless, but it's still constrained to go straight in the universe. And straight in the universe means it has to follow the fabric on which it's running.
Yep.
So that's kind of how you think of it.
Yeah, there is a very good video on YouTube. I don't have the link right now, of a professor in his class who has done exactly what Mark mentioned. He took a long, big, stretchy, like a rubbery sheet, and then he placed a heavy ball in the center, and then he pushes marbles around the object in the center to demonstrate what's called a gravity well. It's very intuitive. It's very instructive. Looks cool to do it. And there's also an applet out there, or there was. It was from a college, might have been the University of Colorado here, where you can play with it. You can set different objects in motion in this gravity well and see whether you can create like a successful orbit or not. I haven't seen it in years. I bet it's still out there somewhere if anybody still uses applets. It's tons of fun to play with. You can see if you can build a a stable solar system or planetary system, whatever.
Oh, well, that sounds like universe. Was it universe simulator? Was it no? Was it? What's that thing we all have here that we play around with? It is called Universe Sandbox. Universe
Yeah.
Sandbox 2, actually.
Yeah.
And that's one where you can actually, in a very high-end graphical environment, we've done this before. Keith from P&K and I did this on one of our streams, where we actually created a solar system. Okay, what would happen if the sun became a black hole? We would continue to orbit just normally. Nothing would happen. We wouldn't get sucked in.
Right.
People were amazed to see that. And because it's not like suddenly it becomes a vacuum cleaner, okay?
Right.
It has the same gravity it always had. It's just now a singularity, and black, basically. Things like that. So pretty cool. And I don't know, Amanda, if you got more questions. That's
I do. I was going to say, then what's an accretion disk? I was wondering if that's what the accretion disk was.
Accrete just means to pile up, to build up, and that's all the matter that's falling toward the black hole just piles up into a ring outside the black hole's event horizon. It gets extremely hot, as they mentioned during the presentation. You're talking like billions of degrees, and that emits. We've talked about black body radiation before on Mark's stream. Well, its peak output is probably in X-rays, I would guess, at that temperature, X-rays or gamma rays.
Sure.
But it radiates at all wavelengths, including radio and visual.
Yeah, and the other thing is, no one's asked. At least I'm not on Mixler right now to see, but I should be able to go there in a minute. You notice that the one side is brighter than the other. You notice that? And that's not data. That's not bad data. That's actually what it really looks like. It looks like a crescent moon, essentially, where one side is very bright and the other side is not very bright. And what that is that's something that's giving away the rotation of the black hole. What's that mean? It means that these photons are actually circling the black hole in a certain direction, because that's the accretion disk that Daryl was just mentioning. That sets up this rotation. So whichever way it goes, the particles that are coming toward us, think of them, and they're light. They're light. Okay, so I say particles because light acts both as a wave and as particles. So when we talk about photons, we're talking about quote unquote particles of light, essentially, not light wavelengths yet. So if that light's coming toward us, then what happens is, just like with the Doppler effect, the light is blue shifted. It's made to be more high energy as it comes toward us. The light coming toward us is also, higher energy than the light going away from us. The light coming toward us is moving faster and is shifted, and the light going away from us is slower and is also shifted, thus in the other direction, the red shift. So you might say, well, why isn't it blue and red? This is a radio telescope. in a different telescope that could see those colors, then maybe we would see the difference in the colors, the high energy versus the lower energy. And what we're seeing, though, is that circulation. And the brighter areas indicate areas where the photons are coming toward us. And that's why we expected to see a crescent. And the simulations were actually remarkably close to this image. The simulations of a black hole, which tells you something. Now, for the conspiracy guys out there, it tells them, aha, this is what they were trying to generate. This is all fake. That entire image is CG, computer generated. Well, it is actually computer generated. And and every single one of the scientists on the panel will tell you so, because it was all integrated together by computers doing elaborate crunching of the algorithms to make sure that it gets the right result from the data presented. No, they said from the data presented. That's the important part. So the brighter crescent side is the light coming toward us. It's moving faster, higher energy, and the light going away from us, slower and lower energy. Right? And it all has to do with that gravity well created by that massive gravitational force in the center that is, black. Really historic. Because that is exactly the kind of thing that we've never been able to see, ever.
I As usual, I'm a little hesitant to talk about cosmology. I think they've kind of gone astray, but I remember reading years and years ago, whatever the popular theory was at the time, uh, about black holes, their density, and their event horizon, and this will vary due to the mass of the black hole. The black holes, if I remember correctly, only have three properties we can determine: their mass, their charge, and their spin. Okay. Uh, if you were to cross the event horizon of a relatively small black hole, you might have heard the term spaghettification before, that it'll stretch you out and tear you into your component atoms. A small black hole, well, you cross that event horizon, you might get torn up pretty quick. But one of the points they made in this idea years ago was that black holes aren't really infinite density. That is the event horizon itself. Inside the event horizon, it's not necessarily infinitely dense. That's only when you get to the singularity at the center of the black hole. And the bigger the black hole is, the less dense it is inside that event horizon. And they postulated as an extreme case that if you took all the matter in the universe and put it into a black hole, well, the density inside that event horizon approaches remarkably well what the density of our universe on average is. You know, it's mostly empty space out there with little chunks and bits of matter and energy flying around. And what that means is we might actually be inside a black hole. So there.
Yeah, let that sink in, folks.
Oh,
That our universe is actually the inside of a black hole. And that's why we can't get out to other universes,
wow.
because we're inside the event horizon. Think about that.
So, okay, to simplify it for me, what is the event horizon? Where the outside of the universe meets the black hole? Like the touching point?
Well, the event horizon is the point at which escape velocity of the black hole meets the speed of light. Okay,
Hold on, say that again.
The event horizon is the point outside the black hole, the shell around the black hole, at which the escape velocity, just like if a rocket launches from Earth and goes to the moon or goes to Jupiter, it has to achieve a certain velocity to get there. The event horizon is the shell, the point around the black hole at which the escape velocity exceeds the speed of light. Nothing, not even light, can escape from inside the event horizon. Does that make sense? Because it's greater than the speed of light, and light is the fastest thing we know of.
And actually, the way I think about it is, once light that's tightly orbiting the black hole, once it ends up being pulled into that, and when I say pull, let's be very careful with our terms here. It's like a whirlpool where all things tend to go toward the center in the whirlpool. You don't just continue going around and around and around. You tend to go toward the center and then down the little, down into the whirlpool. Well, the same thing with light. It's orbiting closer and closer and closer. And then that photon ring just above the event horizon is a very tenuous place. The photons are just as likely to get pulled into the whirlpool, so to speak, or escape. The ones that escape are the ones we see. Okay? The ones that don't escape, well, obviously we don't see them. So those that did escape give us the images that we saw today. All right. Now, in terms of the event horizon is actually that location where, when the photons are spiraling around above the black hole, they get to that certain point where escape is no longer possible. Meaning, not because the gravity is too strong, but essentially that's true. It's because space is warped so much that at that point they just they go around and around and around within the same space. They never escape. There's
Exactly.
there's a likelihood that they can get away, but many will get trapped in that spiral, and some can get away. Those are the ones we see. But once they get a little closer, there's a logical location based on the mass of the black hole, right? And you can calculate the diameter of the event horizon. In fact, we've done that before. And based on that diameter of the event horizon, the objects, the light particles, if we talk about them this way, will be pulled into or migrate and spiral into a location where they can no longer escape. The probability of escape is 0. All right. And that's because gravity has warped space so much beyond a certain point that those photons can no longer go anywhere else but stay within that location. And that has become known as the event horizon. And the diameter of the black hole is that manifestation of that point.
Yes.
Okay, so what's warping space?
Mass.
Yeah, the gravity induced by the mass of the black hole.
Yes. I want to go back to Sagittarius A star, the black hole in the center of our galaxy. Well, it's millions of solar masses, I think, not billions like the black hole in the center of M87 is. But they have imaged, if you look on YouTube as ever, there are animations there and other places of the stars that orbit the black hole in the center of the Milky Way.
Mm-hmm.
And we can't see the black hole itself, of course, because it's black and it's fairly quiescent as such things go. But we can see, we have recorded stars in the neighborhood of Sagittarius A star that are orbiting something very massive, and because of that, they're moving very quickly. You can actually, there's 12 or 15 stars in the neighborhood, and you can watch them over time actually orbit this black hole. It looks really cool. There was a large cloud of gas that fell toward the black hole in the last year or two, and they actually imaged this gas as the cloud was destroyed as it got sucked into the black hole. Most of it went into an orbit around the black hole, which became an accretion disk, but some of it went into the black hole. It's really fascinating to watch. If you just look for on YouTube, probably Sagittarius A star or
well, actually, I can give you the exact name because it's something that I did watch. It's called Stars Orbiting the Black Hole at the Heart of the Milky Way.
There you go.
It's that simple.
And it's really cool to watch, and we've actually seen this in the past, and hopefully with the new Event Horizon, synthetic aperture telescope, we're going to get to see a lot more of it.
And don't forget also that that video that you'll watch, if you go look at that video, and again, it's Stars Orbiting the Black Hole at the Heart of the Milky Way. Okay, and it's on YouTube. When you look at that, you're going to notice that there's other stars in the image that actually show kind of a weird fringing going on. That's an artifact of the many, 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 many frames and time and dates over which these images were done, because it takes some very long times for these objects to orbit. But because they're moving so fast, as Daryl suggested, we could do it. And you can actually see, and this particular video was courtesy of the European Southern Observatory, I believe. And it's from the Very Large Telescope down in Chile. Mm-hmm. And it's just a beautiful video that is just gone unsung because, it's not a bank robbery, it's not a murder, it's not, it's science.
Yeah.
So it actually is distinct proof again of a black hole at the center of our Milky Way. It's right there.
Yeah, and you can see on these videos, the closer orbiting stars are to the Milky Way, the faster they orbit. Yeah. There's one or two that are doing hot laps around a black hole like you would not believe. It's the orbits appear to be highly elliptical. It may be just a matter of our point of view toward the plane of that star's orbit around the Milky Way, whether it's actually more of a closer to a circular orbit or really highly elliptical. But it's fascinating to watch because some of these stars, I mean, they're just zipping like you would not believe.
Yeah, and there's one particular star, the brighter one. When you watch this, you'll see it move in what is a tremendously elliptical orbit, as Daryl said. And as it gets closer to that central point, that's where that's called its semi-minor axis. Is smaller, and then it's actually at the end of its semi-major axis. Right, one of the focuses of the ellipse. It actually accelerates tremendously, like in this last second, zoom right around. If there were planets around that star, they wouldn't know any different. They're still going along in their merry way. They wouldn't recognize that they're being accelerated or not. They would just continue to get pulled along. But if it goes fast enough, then it could actually disrupt that star system, if there was a star system there.
Yes. May I try to take a shot at a question Mark the Shark asked in the chat room?
Sure.
What shape is a black hole? Does it bulge, have a center of mass? Well, as I mentioned a few minutes ago, we can only determine three properties of a black hole, as I understand it. That's its mass, its spin, and its charge. Mark, that can vary with the black hole, or theoretically at least. If the black hole has little spin, it's and we're talking the event horizon here, it's going to be spherical, roughly. Okay. Does it bulge? Like if you look at the planet Jupiter, is noticeably oblate, not round. Yeah, if the black hole's spinning hard enough, it bulges. Does it have a center of mass? Absolutely. I mean, that's by definition what makes the black hole is the center of mass. Some ideas that come from all this is uh, under certain weird circumstances, some speculate that the black hole could actually have a ring shape to it. The event horizon is shaped like a donut, okay? And some people speculate that we could fly through the center of that donut hole and wind up somewhere else that they could actually theoretically use it as a source of propulsion for a starship. That you fly through the center of the donut hole, you're not entering the event horizon because it's to any side from you. You fly right through the center of that donut hole, and it could throw you someplace else in space and time.
Yeah, perhaps. Who knows? We don't really even know.
Well, yeah, and this is true. And again, this is one of the reasons that, cosmology, I have very mixed feelings about. But that's the idea.
Yeah,
I hope I answered your question, Mark.
Very cool. Okay. See, you guys are talking about so many things, it's touching on some of the other questions I had. So if I'm repeating myself, I do apologize. I just want to clarify. Okay, because something that was said, that this black hole spins clockwise, and I didn't realize black holes spun. So, and one of the images they were showing, I guess it was the photons going, it looked like they were going from behind the black hole, at least in some instances, towards us. I assume that's what was making the images. From some of the telescopes anyway.
Yeah. Go ahead, Mark.
All right, well, you're watching the photons orbiting the black hole very, very close to the event horizon. It's very hot. They're very energetic, and they are either spiraling down into the black hole, or future photons are going to spiral into the black hole, or they're going to escape. The ones that escape, of course, didn't spiral in, but a good portion do spiral in, and a good portion escape. Because it can go either way at that point. That's the photon sphere around the black hole. Again, the ones that come toward us, that are captured coming toward us, are actually coming at us at a very, obviously, light speed, of course, but they're accelerated because of the fact that they are coming toward us. The ones going away, and Doppler shifted as well, and going away from us, they're slowed down. And again, that has to do with the way gravity has distorted the fabric of space at that location. And black holes change everything about the way you think about the universe. It's not just a simple, speed of light is the speed of light any longer. You know what I mean? There's more considerations. And I like Daryl's explanation. He did a good job with that, I think, for Mark the Shark.
Amanda, I want to back up on what you said a little bit. You didn't realize that black holes spin. Well, when you go out and you look up in the sky at night, every star, every planet, every galaxy, everything you see is spinning.
It's in motion, yeah.
It's conservation of angular momentum, okay? And to go to the old analogy, if you ever watch a figure skater, she's out there spinning on the ice, pirouetting, that the closer she pulls her arms into her body, the faster she spins. Okay. She pushes her arms out, she slows down. She pulls her arms in, she spins faster. The very same thing happens out in space. When stars collapse and form black holes, or neutron stars or black holes, all that mass compressing toward the center, well, conservation of angular momentum makes that object spin faster. There are neutron stars out there, we might call them pulsars, that are spinning like 1,000 times a second. Okay, they are spinning that darn fast because all that mass contracted to the center, just like that ice skater did when she pulled her arms in. Does that make sense?
Mm-hmm.
So this is why black holes, neutron stars, you name it. I mean, we look at our star, the sun. It takes, if I remember correctly, about 25 days to complete one spin, 1 day on the sun, you could call it.
And that's pretty slow compared to some stars that they move so fast that their equators are actually bulging.
Yes. Again, like Jupiter, it becomes oblate. Some stars are spinning so fast they're almost tearing themselves apart.
Yeah, Pleione in the Pleiades
Yep.
is an example of that, and Vega's another example. But it's actually its spin is high. It's slightly oblate, but it's not tearing itself apart in any way.
But this is why black holes spin, and when they spin, they usually spin pretty darn fast.
Yeah.
Okay, so if some of the light from the accretion disk gets sucked in through, and I use the term loosely, gets sucked in through the event horizon into the black hole, that doesn't necessarily add mass to the black hole? Is that correct?
That is correct. It actually, for it to add mass to the black hole, it would have to suck in matter, such as having a star nearby that gets, like, if you look at that, stars orbiting the black hole at the center of our Milky Way video, you'll see a star that may possibly, if it encounters any kind of drag effect from the black hole, could spiral into the black hole eventually, and all that matter will add the star's mass to the black hole. And no more, it'll only add that star's mass. Mass isn't created from nowhere. It has to come from somewhere. So it would only be
this is going to be a basic question. Is light not matter?
Does
it not have mass?
Light.
You're opening a can of worms here.
Well,
again, but it's okay. We can talk about this because photons. That is to say, light does not have mass in the classic sense. We can treat it as if it does by looking at what gravity causes it to do. And it has to do with what I said before. It's warping the fabric of space. So we're actually indirectly looking at the warpage of the fabric of space when we see light bending around things. Okay? The sun's gravity warps space in its vicinity. So light during an eclipse, stars they're coming from stars at a distance. Light during an eclipse will be bent a little bit. Light from stars beyond the sun will be bent. And that's actually an experiment that was done to confirm Einstein's theory of relativity there. That the bend would occur, and it did. And just as predicted. So Einstein may have had a few things that he was wrong about, like saying we'd never detect gravity waves in our, because he didn't suspect there'd be anything that could do that. Um, that is to say, in our local universe, but it turned out there was. We saw two black holes collide, and they generated gravity waves, and the LIGO detectors, all over, three of them around the world, the two LIGOs, and one in Hanford, Washington, one in Louisiana, and one in Italy, the Virgo instrument in Italy.
Yep.
These are interferometers, long baseline interferometers, and LIGO stands for Laser Interferometric Gravitational Wave Observatory. Okay, so that's what the LIGO detectors were, and they detected these waves passing through the Earth, and the fact that they passed through at slightly different times showed exactly where it was. We could triangulate where it came from because of that. So it's really cool, and but it's the way that gravity warps space that makes light take a different path. And it's not that light has mass. Boy, that's hard to get through, I'm sure.
I'm going to play devil's advocate here for a second. Einstein's famous equation, E equals mc squared, which means that energy equals mass times the speed of light squared. There is a relationship there that a little bit of mass equals a whole lot of energy. Okay.
Mm-hmm.
I mean, the speed of light squared, boy, that's really going to jack up the numbers. This is where it gets fuzzy and beyond light itself, which, a photon is a massless particle. It moves at the speed of light. It has to move at the speed of light because it has no mass, but there's energy there. Okay, and you take enough of that energy and pile it up, and it's going to be equivalent to mass. I hope that makes sense. It comes up with neutrinos also, that are neutrinos truly massless, or do they have a tiny, tiny bit of mass to them? Neutrinos move at or very close to the speed of light. Neutrinos are emitted by the sun. Neutrinos are emitted by every star, every black hole, every neutron star, whatever.
That's right. Yeah.
And there are billions and billions of neutrinos sleeting through every square inch of you every second.
That's true.
I have often wondered if neutrinos might not qualify as the missing matter or so-called dark matter. I thought it was interesting during the presentation that one guy actually asked about dark matter. He must not have got the memo. Mark, you mentioned this recently, that, well, now all of a sudden some astrophysicists are saying that there is no dark matter. They never knew what dark matter. I'm sorry.
Yeah, they said it's possibly been identified. Yeah.
Okay. Well, I have a problem with dark matter and dark energy. We don't know what it is or was, if it ever really existed. I have my doubts personally, and again, this is why I have problems with modern cosmology.
Perhaps you could have gone down the path, and maybe we're going to go down the path that says that, dark energy, for instance, has been used to explain why the universe seems to be accelerating in its expansion.
Yeah.
Now, we have a lot of mass inside our universe, okay? All the stuff that came from the very beginning, right? Well, as it expands outward in this spherical explosion outward, or roughly spherical, we don't really know if it was a totally spherical explosion, actually, then you would think that maybe the mass inside would slow down the expansion and maybe cause it to stop at some point, and then maybe contract and come back and do it all over again as it comes back, because like a rubber band. You throw a ball out on a rubber band, and the rubber band stretches to its extent, and then the strength of the rubber band says, now you come back, and it comes back. Well, that strength of the rubber band is the mass inside the universe. So if that was the case, should we see that? Well, it turns out that what we found was completely different from what we expected. We found that the universe is not only expanding, which is fine. Maybe we're still in the expansion stage. It's actually accelerating in its expansion. The expansion's increasing. The Hubble constant may be wrong. There are a lot of things may be wrong with the way we thought about the universe. So what did they suspect? Well, they suspected that maybe there's this anti-mass material on the other side of the universe's border, where it ends, called dark energy, which is actually attracting the stuff inside outward at an ever increasing rate. And there's models to show how that can, live within our minds in a way that makes sense. But it does seem to be a bit of a stretch to go down that path. And eventually we'll figure it out. I mean, technically, in fact, I'm going to be talking about dark energy and dark matter on my talk in Arkansas. That's one of the things I'll be talking about. And one of the things I'm going to mention is that, dark energy comprises, currently, it's 74% of what we believe the universe is. And as Daryl said, dark means not black. Dark means we don't know what it is. So it's just as sensible to say unknown matter, unknown energy. Okay. They just thought that two syllables weren't as dramatic as one, so they call it dark. Lights are still off. We can't see what's in the room, basically. So
Yeah.
So in terms of dark matter, though, some recent studies turned up this filamentary structure that exists between galaxies that might explain all the dark matter. Now, if it wasn't for fast radio bursts, which we talked about on SkyTour Radio, if you recall, if it wasn't for fast radio bursts coming to us from many tens of billions of light years away in other galaxies, then we would not have known about this material between galaxies. We thought that classically that the universe was sort of empty between galaxies. And guess what? It's anything but. It's full of other mass. And we say gas is made of atoms. Atoms have mass. Okay? So it turns out that this filamentary structure that we see in between galaxies is something that was detectable. And the way we detected it, the only way we could detect it, because it's not visible to any of our telescopes directly, is by what happens to other energy that passes through it. And that other energy that really pointed this out to us were these fast radio bursts, which were those millisecond pulses, some that repeat, that come from distant galaxies. Millisecond pulses. Some people thought, well, are those extraterrestrial signals? Well, if they were, there would have been a lot of energy. Okay, but as those fast radio bursts reached us, they had already passed through all this intervening, quote unquote, space between the galaxies. And it turns out that what reached us was very different from what was likely emitted. And the reason was that the matter between the galaxies changed the nature of that energy, that light that was coming toward us. And it caused the light to be sort of spread out a little bit. And that spread is called the dispersion. Okay, dispersion. And this dispersion is something that we could measure. And we look at all the FRBs, the fast radio bursts from all these different places. There's only like 90, just over 90 that have been seen so far. And they all have a dispersion that shows us that there's matter out there. Something caused the light to change. And it kind of gives us a very crude map of the matter between the galaxies. And it turns out that there's quite a lot of it. So with extrapolating for the rest of the universe, a team decided to figure out if that meant that the missing mass was found. And to their credit, they think it has been. So that's the reason why the dark matter concept may be a non-item, but it'll probably be 5 to 10 years before that's even confirmable. Maybe sooner. I know they're working on trying to figure that out now, but there's only just so many FRBs that occur.
May I add something to this? I have seen recent speculation since all the second thoughts about the nature and existence of dark matter came into question, that they're falling back on maybe there are a whole lot of black holes out there in the universe which make up the dark matter. It's still speculation, and again, this is the how many angels can dance on the head of a pin?
6.
7. Well, the answer is 42, of course.
Of course.
If you ever read Hitchhiker's Guide
Yes.
to the Galaxy.
Douglas Adams.
but in the end, we don't really know. We don't really know what dark matter is. Me personally, I don't know that it exists. I'm still old school. I've said this before. You talked earlier about the rebounding universe, or what they call the oscillating universe model. This is the whole yin yang thing, that, well, the Big Bang happened and everything is going to recycle back into the Big Fall. Uh, I just like the idea of that because it sort of satisfies me philosophically. And, it has a cyclical nature, which I think could be appealing, even if ultimately it doesn't mean, it doesn't say anything about us surviving uh, in the very long term.
Yeah.
I hope that makes sense.
Okay, still back to the accretion disk and the event horizon. Is it possible then that a black hole could eventually suck up the entire accretion disk? Or will there always be some photons out far enough that it won't get to that
Well,
event horizon?
that
Uh,
okay, Daryl, go ahead.
I'm sorry. Well, Mark mentioned earlier that if our sun magically became a black hole, it's not going to suck us inside it. It's going to, the mass, whether it's in a sun or in a small black hole of a solar mass, we're going to stay right where we are now, orbiting it. We're not going to get pulled in. It's just the mass. It is what it is. That accretion disk orbiting outside the event horizon of the black hole, I dare say all the energy of that mass, that is its motion, you're going to have a whole lot of collisions of, the particles in the accretion disk, that some of them are going to get slowed down and some of them are going to pass the event horizon. They're going to fall into the black hole. But as a general thing, it's going to maintain a fairly stable orbit outside the event horizon. The accretion disk is.
Okay, I think I'm starting to understand how this all works.
Yeah,
Yeah.
no.
Like I'm understanding what you guys are saying, and it's making more and more sense. But I think I've got a pretty good grasp on this now.
Cool.
I hope so.
Okay. Well, I hope so too. Now, if I can just remember it for next time. I liked one of the illustrations they played during the stream, where it was the black hole and all the, I guess, photons going past them from every direction, actually making the roundness of the black hole for us to see, for us to image. I don't know.
Yes.
For
Well,
those
yeah.
for those watching, I don't know if that description made sense, but that's the accretion disk. The parts that don't get sucked in are the accretion disk. Yes.
Well, the part of the accretion disk, yeah.
Okay.
And the accretion disk, you're not seeing the full accretion disk there in that image. You're only seeing the
Just like
photons.
pictures.
You're only seeing the photons that escaped to get to us. You're not seeing
All
you're
the
not
ones that went around close.
you're not seeing you're seeing those only. You're not seeing the ones that are that ended up obviously going inside.
Mm-hmm.
Okay, but again, an accretion disk is just that, a disk. And around the center of the black hole, there's going to be like a halo of these photons going around, and then there will be they'll tend to go out into a disk actually because of the angular momentum that's they have as they go as they're getting pulled toward the black hole. As again they're following space, and space is warped, so the photons are actually going into this gravity well like they're supposed to. And again, you just got to think of that flat sheet with a bowling ball in the middle.
Yeah.
And rolling a marble from a distance, and you actually see how it swirls around the bowling ball, or just go straight into it. If you just let it go from the outside, it go clink, it'll just hit the bowling ball directly every single time.
But the only way for space to warp is for that black hole to get more mass.
To warp more.
Well, that's what I mean. Like, if it's warped to a certain degree, like what holds it there? Why doesn't it keep warping?
Because the mass determines how much it warps. If the mass increases,
Yeah.
it warps more.
Yeah. Okay. So it would have to
acquire more mass.
Yeah.
Be a
Okay.
deeper warp.
And but if it had more mass, then it would warp more space, and it would
That's
it would have a further event horizon.
No, the same event horizon, but you mean further, meaning a larger event
Larger,
horizon?
yeah.
Yeah.
Larger diameter event horizon would happen with more
Yes.
mass.
Okay.
As I understand it, and that image again matched pretty well, I think, what they showed in the movie Interstellar, though I have yet to see it. But when you look at that, you might say that the bigger, fatter part of that light toward the lower part of the image might be the actual accretion disk on our side of the black hole that we can see directly. Uh, the light, which is comprising the upper part of the ring around the black hole, the skinnier line toward the top of the image, that light is actually being bent so much in the local gravitational field that light you see is coming from the far side of the black hole.
That's a micro lensing event of the light itself, actually, but it's sort of a macro lensing event. It's massive gravity.
There you go.
Yeah, remember we talked about micro lensing? In fact, I'll be talking about micro lensing actually this weekend as well in Arkansas, and it's where you have for finding exoplanets, we can use the gravity that the exoplanet has and how it warps the local space around it as it's traveling around its star. And a more distant star's light passing by that planet will have its light warped just a little bit as the photons follow that gravity well. And when they do, we can catch that, and we have, and that's how we found planets using microlensing as well. So, gravity has a very big role to play. We're living inside a gigantic fabric, a three-dimensional fabric of space. And that's why showing it with a sheet and a bowling ball, it's one dimension. It's not even, to me, it's not the way it really should be represented. So when we see that there's light on all sides of the black hole, this analogy of the sheet with a bowling ball doesn't work because you can't see how that could work. But you can understand that if you had many of those sheets going in every single plane, all the which way, every which way around, then you'd see that many orbits could be established, and you can see how this light could be bent from the backside and come back around like that. And again, it's a micro lensing event once again.
This one actually came up in P&K chat. P&K Space Imaging chat. Please check them out on YouTube. Now, I don't know if this is true. It sounded like it was a legitimate question and not someone just being a troll. They wanted to know, they said dust can escape, but light can't. Is that true? Can dust escape a black hole? I'm not sure. It seemed like a legitimate question. Like it wasn't someone putting us on, So I wanted to ask why they thought that.
It could be just someone who doesn't understand.
Mm-hmm.
Dust is even less likely to escape than light. Light is the fastest, nimblest thing in the universe besides neutrinos, perhaps. And dust, of course, is mass. And if the mass is orbiting the black hole, and if it's undergoing collisions with other dust and so forth, it just has to be slowed down a little to come closer and closer and closer, and finally go across the event horizon, which for it doesn't really matter because the dust is feeling a gravitational pull all along, and at the event horizon, the dust is going to get ripped apart into its constituent atoms probably, and once it gets into the event horizon where the gravity is strongest for the tidal forces to disassemble it, then it just adds to the mass of the black hole and continues to, that's how that works. I mean, light, again, is, we consider it massless, okay, but the way gravity warps the space that light follows makes light look like it's following, being affected by the gravity that way. It's a two-prong approach. Light's not being affected by gravity directly. Light is reacting to what gravity has done to space.
See, something I had written down is what caught the pictures, but then it was telescopes from around the world, so I got that part. It was M87.
Yes.
Yeah, and it was okay because we see a jet at about 2 o'clock. Is that right?
Yes.
It's
Yes.
about
Yeah.
2 o'clock.
Yep.
Yes.
In our
So
I mean, if telescopes reverse images, it'll be at 11 o'clock. And if they spin them upside down, it could be at
yeah,
7 o'clock.
from our telescope though.
Yeah.
Well,
Yeah.
Conventional view is north at the top of the image. And if that is indeed the case, and I think it is the case with your telescope, correct, Mark?
It is. We're seeing
That-
the clock.
Yeah. If convention holds and north is at the top of the image, well, the jet appears to be at about 2 o'clock.
okay, cool. And for those that want to know what we're talking about, please subscribe to Sky Tour live stream on YouTube. Hit the bell.
And I just
Yeah,
want to mention, I just want to say one thing too. For Charles mentioned what he's listening to. He missed. He must have missed the NASA presentation of the first image taken by a group of submillimeter radio telescopes around the world that they've been putting together for months, years. And it was the picture of the black hole in the center of the galaxy M87, an actual photograph showing a black disc-like structure. Black round structure that's the event horizon of a black hole. And that resolution allows them to actually measure the size of that black hole. And the reason is because they're using the entire Earth, because these telescopes are fixed in fixed locations on the Earth. These telescopes were imaging this black hole in the center of M87 in the radio spectrum. And as Earth rotated, they keep imaging, and they're sweeping out a path, basically building data for a virtual mirror of the diameter of the Earth. And there's many telescopes that were involved in this. All that light was integrated over time, and then there was one procedure to put all those telescopes' light together and form the final image, and that's what we saw.
Is it fair to call that a photograph? This is the thing I've always had about imaging from radio telescopes. As they mentioned during the presentation, when they collected all the data from all the telescopes, they had petabytes of information that they had to crunch down and integrate and make that image. And again, I was not surprised at what it looked like because, well, just to see the nature of that image, it looks like a radio telescope image. There's a whole lot of number crunching going on to build that. It's not just a snapshot.
Yeah.
And this is where I question whether it's really fair to call it a photograph.
Well, I mean, it's a computer-generated photograph. And the conspiracy folks will say, aha, it's not real. Actually, it's very real. You're looking at a representation of what the radio signals told us. And it wasn't a matter of making the radio signals match what we think it should look like. It was a matter of the radio signals telling us what it actually looks like and seeing how well it agrees with what we thought it looked like.
Uh-huh.
And we have powerful computers that can simulate powerful gravitational fields and black holes, and thus the energies that are given off by photons in the photon sphere around the black hole. And what we saw today was an image that's very much like what has been simulated. And confirmation, that is, that the algorithms used to generate that, what we thought it might look like, the simulated view, again, drawn from Einstein's theory of general relativity, were correct. So this is why they were saying it's a vindication of Einstein's theory of relativity, okay, and actually theory of gravity mostly. So, the gravitational particulars. So that was, to me, probably the best result. Seeing the image was great, and Daryl and I probably expected to see about the same thing. We did.
I had no idea what to expect. It just sounded exciting.
Most people didn't. Most people were kind of disappointed that it was sort of fuzzy. But when I saw the black disc that you saw on the screen, that was the most amazing part. Yes, it was fuzzy on the edge because of resolution, because you had multiple telescopes imaging over a long period of time. M87's black hole changes on the order of a week, at a time. So it's important to understand that because of that, they had to decide, you know, what data they were going to use for one, which data they would integrate number two, and how they were going to put it together so that it made a meaningful image. I'm sure if they show the intermediate images acquired over time, you'll see this tremendous variation on what it actually looked like over time,
Oh yeah.
and they have to
Well,
reject bad data.
well, how long do you think these images are being processed for? Like, do you think these are days at a time or just hours at a time? Because if it changes over the course of a week, wouldn't wouldn't like a few days long of a stream of a image be too long? Wouldn't that kind of guarantee a fuzzy image,
Um,
if you know what I mean?
I do, but then again, just like our telescope and Skytour live stream, we follow the stars, and those telescopes can follow the stars as well. So they could do long exposures if they want to, but I'm not sure how long the exposures were in the submillimeter telescopes. I don't have any idea
Yeah.
of how long each of those exposures were. When we say exposure, I'd rather say integrations, okay? Because when you're bringing in data like that, and just doing basically uh, photon counts in the radio spectrum, okay, the radio wave spectrum, those are integrations, and you're just getting a number. But it's a number from a particular spot in the sky, and that tells you the data you need to know. And you do that over and over and over and over and over, and you finally end up building a picture. So basically, that's what these telescopes have done. That's why it took so long. And I don't know how long each individual integration was.
Hmm.
I would like
Oh,
to add something to this.
yeah, go ahead.
Well, this has to do with the nature of radio imaging, quote unquote. The colors they chose, for example, was there any real information that made them color it that orangish yellow? Or is that just, did somebody just make a random decision what color to paint that image? Radio has no color, okay? They had to bring that down to visible wavelengths to have something to show us. Uh, I am imagining here, what if we could magically place a large telescope at the approximate distance or magnification that is shown in this radio image? If we could place a visual light telescope at a similar distance, so we would see that black hole at the same image scale. Invisible light, what color would it really be? I assume it would be white hot.
I would
Uh,
assume it would be actually.
yeah,
But
yeah,
then again, that's only for the photons that reach the visible spectrum.
yes,
Um, if it's if it's that hot, then most of that energy will be in X-rays, and you may not see it at all. Yet,
exactly.
yet you're getting pummeled with X-rays.
Yeah,
So we'd have to be really careful, because invisible light can kill you, as you know. Too many X-rays, you can get cancers, right?
oh
Uh,
yeah,
it disrupts the cells and causes these catastrophic chain reactions of destruction. But the fact is, when you look at a black hole in the visible light, what would we actually see if we were close enough to see it? We might see the way we see some light, because some of the light, prior to being accelerated and heated to superheated proportions, would be in the visible spectrum, and we would actually see that. We would probably see.
excuse
Okay.
me. I'm sorry. That snuck up on me. I couldn't mute in time.
No
That was,
worries.
it sounded like Daryl was going, "Yeah, bull crap." I think it sounded like that. Yeah,
No,
crap.
sorry. I'm sorry. I
I know,
apologize.
kidding, Daryl. It's more like like we'd probably see a little bit of the accretion disk. If there's matter in the accretion disk getting heated up, we'd see it, and we'd first see it probably in the infrared, where it would get heated up to be very hot. And so we'd probably see an infrared accretion disk. And if some of that light was raised to the point where it was matter, say the matter was hot enough, then it would probably also be detectable. But again, unless there's something to generate visible light, we won't see it.
Yeah, and this is the black body issue I raised earlier that, the hotter the object, it's going to radiate at all wavelengths. but the higher the energy, the higher the frequency,
Yes.
the more blue you could say the light is going to
Yes.
be.
Until it's
Uh,
right out of the
and
visible spectrum entirely.
exactly, and that's where the stuff is so energetic that it's putting out X-rays and maybe gamma rays. Uh, we talked about this recently on one of your Sky Tour live streams, Mark. That dumb Disney movie, The Black Hole, from
Yeah.
back in the late 70s. It was
I remember.
Disney's answer to the first Star Wars movie.
Yes.
It was a really stupid movie.
Showing a big whirlpool in space. Yeah.
Yeah, but uh, I think I mentioned before that I remember I saw Siskel and Ebert's review of the movie. And Ebert goes, well, duh, the black hole wasn't even black. Okay, it looked like a great big blue whirlpool swirling around this black thing down in the middle, and it even looked sunk in the middle, like the bowling ball on the sheet. But as they understood black hole physics at the time, it was actually not a bad representation for the time of what a black hole could look like.
Yeah.
And that was really about the only thing they did get right in the entire movie. Excuse me.
I would. You're right, because they were seeing the concepts. I mean, when they reviewed the movie and they were doing the movie, they were trying to figure out, well, how do we represent a black hole? And everyone told them, well, take this big sheet of rubber and put a bowling ball in the middle. And that's where it started. And thus they thought of that, and it got to the art director, and the art director said, okay, I want a big well. Okay, we have this gravity, we have this big spiral. Let's do it that way. And then we imagine there'll be some light emitted and all that. And it became a very bright place that you could see very, very clearly from the Cygnus, which was the ship in the black hole. Not that I've seen it 6 times. But anyway,
Right.
look, it was space. It was bad science fiction, but it was all we had. So, hey, give me a break. So, and I think that that is what became the classic. That became the classic image of a black hole.
Yeah.
And it's a way to it's a helpful metaphor to understand how a black hole affects light, but it's not a helpful image to explain how a black hole actually looks.
Yeah, and that goes back to what I was wondering a minute ago about, if we could take a visual light image of M87 comparable to, the magnification or the effective distance to the black hole that they showed in radio wavelengths, what the black hole really looks like
Yeah.
in
Nice.
a way that we could actually see it.
Yeah. Yep. Very much so, and it looked good. I mean, it was a very nice image. Again, nothing I didn't expect. I expected to see something like that. I expected to see the crescent, with the accelerated and brightened light on one side versus the other.
To me,
I think. I'm sorry. Go ahead, Amanda.
no, go ahead.
Well, I was going to say, still talking about movies. If I remember correctly, when the maker of the movie Interstellar designed the black hole, they went. I want to say it was Kip Thorne, if he's even still alive.
Yeah, Kip Thorne was the consultant. I talked to Kip. I spent a number of hours with him talking about black holes in particular. He's a good guy, and he was the right person to have as the consultant on the movie. And of course, and I don't mean to derail your point here, so don't forget it. I'll get right back to you. But the problem was that he wasn't in charge of all the science, and some of the science had to be kind of fabricated to make the movie interesting. See what I mean?
Yes.
So go ahead, finish your point.
Oh well, yeah. I mean, that's one of the things I guess they got right in the movie. Again, I haven't seen the movie yet. It's sitting right here within about 3 feet from me, but I haven't watched it yet. I have seen images of the black hole from the movie, though, and it looked a whole lot like what the Event Horizon people showed us this morning.
Yeah, and that's because they were using the view from a relativistic point of view. What would it look like if we consider Einstein's theory of relativity? About the only thing that they if you say they got it wrong, the only thing they got wrong in Interstellar, which even Kip Thorne would have to agree, they couldn't do without getting it wrong, is they showed it in visible light. You wouldn't see it in visible light. It would be in the infrared. It'd be in the high energy X-ray mappings. You might not see much at all in the visible light spectrum.
Uh-huh.
Well,
That's the movies versus reality for you, I guess.
Well, that's okay. I mean, either way, it educates people to some extent about black holes, which is one of the things that Thorne is very much passionate about.
Oh yeah.
Where the black holes, and I've mentioned this on Skytour Radio, Skytour Livestream, how when he and I talked, we talked about he had an argument with Stephen Hawking about the fact that Thorne felt that time travel, in a sense, was possible because he set up a situation and he went through the whole thing with all the equations and everything to show how a spacecraft could be entering a black hole and see itself emerging from the complementary white hole at the same time. Now, effectively, that's sort of time travel, isn't it? Seeing into the future a little bit. And so he argued with Hawking that was time travel. And he sent that argument to Hawking, who said, "No, this is baloney." And he wrote, a rebuttal to it. And then they both stewed on it for a while. And Thorne read the rebuttal from Hawking, and Hawking read the theory from Thorne. And then they both came to see the other's point of view, and then agreed with the other wholeheartedly. You're right. You're right. There is no such thing as time travel. You can't do it. You're right. Absolutely, Stephen. And Stephen Hawking wrote back and said, "No, Kip, you're right. You can do it." So you see, this is my point here and I say this a lot, even the greatest minds on Earth cannot sometimes agree when we look at physics so outlandish, so outrageous, and so out of our normal expectation.
I've mentioned the book "Why Does E Equal MC Squared" before, and they get into the concept of space-time, not just space, not just time, but in the sense of relativity, space-time, when you combine them together. And they have a number of what they call space-time diagrams in the book. It's a very interesting book, and they tried specifically to keep it at a layman's level. There is a little bit of math later in the book, but not a lot. But just to show, you have to kind of wrap your head around these space-time diagrams. As I understand it, though, in the sense of relativity and space-time, time is a one-way arrow.
Yes.
And the rest of it, well, as Mark just said, when Kip Thorne and Stephen Hawking, got into a discussion about it, it gets pretty fanciful, and it's way down the road from us. I mean, who knows? Maybe we'll be able to time travel someday. Yeah. Personally, I don't think so, but
it's really not time travel per se, but getting a preview of information. It was more of an information-related thing more than time travel, but essentially you're seeing information you couldn't possibly get to know unless it was you're looking forward in time to see it, basically.
Right. Yeah. And the information deal is, I mentioned this recently on one of your live streams, that again, this goes back to cosmology and what happens to matter. Hawking talked about this, I think, that they look at it as information, quote unquote, and is the information lost or not when it goes into a black hole?
Yeah.
And that's when it starts kind of going over my head.
Yeah.
If you wanted to speak on that, I'd love to hear it.
Well, I know that I know that Hawking and Thorne had talked about the black holes losing information and saying they can't. I don't know anything more about that, and that's it. Really ends up getting too deep here to just. I mean, we'd have to start talking about Hawking radiation and where it comes from. We'd have to talk about what's really meant by a singularity, and most of those concepts are intellectual concepts that are not things that most people can grab onto. And I'm not saying people aren't intellectual. Certainly they are. But it's very hard to discuss these things without having to basically go through and give a college course on all the stuff that requires understanding it. And that's the problem, It's now, as far as saying it simply, basically what they're saying is that when a black hole basically absorbs an object, it doesn't lose the information associated with that object. Okay, and maybe there's something bigger here. Maybe this is related to quantum entanglement. Now, quantum entanglement's a really, really interesting process. We have not actually adequately been able to explain it, and that's why it's called by some spooky action at a distance. Okay, I think that quantum entanglement is probably the crux of the understanding that we're going to need. Understanding quantum entanglement is the crux of, that we're going to need to actually understand how black holes deal with information, because matter can't be created or destroyed. Okay, so in a sense, if that's the case, then all of the information associated with the matter goes somewhere, but where? But where and how would we get at that information?
Yeah.
So for instance, when quantum entanglement was discovered, it was one of these things where they had object A. You split object A into two pieces, okay, A1 and A2. Put the pieces in two different laboratories, essentially. Change the electrons on object B over in laboratory B. Object A's, electrons also change in the other laboratory identically. Now, wait a minute. How can that happen? They're totally separate. Well, the answer was that they're not separate. They weren't separate. They are still communicating at some level that became known as that spooky action at a distance or quantum entanglement. And I think I've said this before. In fact, I spoke a little bit about this in Las Vegas last week when I did a conference there. I think that when we talk about this quantum entanglement process, we also want to consider that the human brain is, and I know I'm kind of deviating a little bit from black holes, but it really is kind of the same thing. We look at the human brain. The human brain is a miraculous organ. Everyone's human brain is made of the same material. Some have more capacity than others. Some have, damage. Like my head has had damage. I've had brain surgery. And some people have superior intellects. But we all have the same capabilities in terms of the capability of the brain. And I think that at the, and this is the word I made up, the brainular level, the level of the brain, I think that when you're sitting in your room and you haven't heard from a friend of yours in 10 years, and you're thinking about that friend and suddenly they call, you say, what an amazing coincidence. We must be clairvoyant. We must have ESP. Okay, that's what we call it now. The fact is, I think it's actually just a scientific explanation waiting to be had, and that's quantum entanglement. When you think of someone, it sends a message somehow through the communication between the brain and other brains, and if you can actually target that information too, and that person thinks of you, and one of you decides to call the other, and that's how that happens. And that is quantum entanglement at the human level. That's how that happens. So perhaps in the future we will learn, again, from black holes, in fact, too, we will learn how to communicate with each other without cell phones. Maybe we will just have a thought process by which we can target specific people. Maybe we can do, right?
I'm sorry. Go
No,
ahead.
go ahead. No, that's basically kind of the end. So we can target specific people with those types of things and talk to people that way.
Oh, maybe it's hormones. I remember my high school sweetheart and I. We talked every day on the phone. This is long before cell phones. That it happened several times to us that one of us would go to call the other, and we would pick up the telephone, and we would hear no ringtone.
Because they're already there.
Right, because the other one had picked up the phone with the same intent to call the other, and
And then you heard the dialing.
yeah,
Yeah, it happened to me too a number of
yeah,
times. Yeah.
and well, we were young and randy, and maybe it was quantum entanglement, but maybe it was just raging hormones too.
It,
I want to go
I'm
back
sure
to
it's a
you.
blend. I'm sure
Yeah.
it's a blend.
You mentioned singularities earlier, and for people who may not be familiar with the concept, uh, when people think about black holes, generally they're thinking about the event horizon, okay, and that black thing in the middle. The actual point of the black hole is called the singularity. It lies at the center of the black hole. It has no size. It is a mathematical point. It has no dimension. But all the mass, all the suns, the gas, whatever, the accretion disk that has fallen past the event horizon winds up inside that mathematical point. All that mass is concentrated down into a point, smaller than an atom. That is the singularity. Now, this is where the speculation comes. Well, when all that mass and energy falls into the singularity, the actual heart of the black hole, where does it go? Where does it wind up inside that singularity? Is it trapped there forever or not? This is where the idea of white holes come from, that
Yeah.
somewhere else in the universe, or maybe in a different universe, that could be equivalent to our Big Bang. That when that matter falls in somewhere, it's going to come out someplace else. And that is the putative idea behind a white hole.
Yep. And I will say this about the singularity. I know that um some the concept of a singularity is weird. Because the laws that we understand in physics and astronomy and astrophysics and cosmology don't exist there. Um, and so, really, we haven't seen inside to see, but I actually have my own theory about what a singularity is. And that is that if we look at the black hole itself, the event horizon grows as the mass increases of the black hole.
Uh-huh.
Okay, but I don't believe that the singularity is actually a very small, infinitely small point. Okay, basically in the black hole. I think that that's a point from which the gravity well is initiated from. But I think that the mass of the objects inside the black hole, I think that they are compressed very, very small, very tightly together in a way that still violates our current understanding of physics, but does not require it to be so infinitely small that it defies our own imagination. I believe that that's really probably, it actually has a diameter, a true value. And I know that the black hole physicists don't agree with this, and I have nothing to go on, other than a feeling that I have, and that's a feeling based on understanding of black holes to the level that I understand them. I mean, I do understand them, of course, because I've worked with them, here and there. But I don't have the same kind of knowledge, of course, that Kip Thorne has or anybody else like that. Definitely, they've made a life of trying to understand the phenomenon. But I might have asked him the question about the singularity because I've had problems with what a singularity is in the past. Because the question is, well, if a singularity is really that small, then we can't discuss matter anymore. But what happens to the information carried by that matter?
Yep.
Is it also lost? And they're saying, well, no, it's not lost. Well, then how can it be a singularity if it's not lost? The data would have to be lost. And that's where you say maybe it has to do with a white hole. Okay, well, show me a white hole. I want to see one. Typically it's going to be very bright, and I don't see any white holes. Um, you know, quasars, quasi-stellar objects, are now galaxies that have very active cores. What are the active cores? Are those white holes? No, they're supermassive black holes. Wait a minute, where's the white holes? See, that's just the black and white analogies there. You know, the black hole must have a white hole, and it must be a counterpart, and there might be a counterpart, but we don't know what that is yet. And that's why physics, cosmology, astrophysics, astronomy, that's why this is so exciting. You know, I have trouble with the singularity as an infinitely small point, and that's where I am at that point. I have not changed that view. So,
I would wonder. I mentioned earlier that they speculated years ago that we might actually be inside a black hole, which
I remember that, yeah. Yeah.
the event horizon basically comprises our, the shell around our universe, so to speak. Though it'd probably be in a higher dimension. This is where the finite yet unbounded thing comes from.
So you're in that place now. See, that's
Yeah,
you're in that.
yeah.
You're saying, well, then the singularity is our entire universe, over 90 billion light years in diameter.
Uh-huh.
That means it's a beyond massive black hole. It's the entire mass of the universe. And but the question is, why would we not be able to see beyond it? We should be able to see beyond the event horizon if we're inside a black hole. See, because that's the other direction. See, from outside trying to look in, we couldn't see. But from inside looking out, we should be able to see everything.
Uh-huh.
See? So why couldn't we? And that's why I've always had trouble with that concept of living in a black hole. You know, I also think, I've heard the theory that we're just because of the CMB, the cosmic microwave background that we see in every direction, 2.7 Kelvin all around us. That's the temperature. Well, because of that, maybe we're just being slowly microwaved in a big microwave in someone's living room, and we're inside a microwave. I mean, I've actually countered that black hole argument with that statement. We don't know. It's as logical as that.
We don't know.
Yeah.
And that's where the angels dancing on the head of a pin comes to. Yep. Anyway, Amanda, do you have any more questions for us?
I do. But I did want to touch, you guys were talking about it a bit a little while ago. When we saw the images, the accretion disk was a reddish orange. So I marked down, does that mean it's not so hot? But you guys are saying that might not be the true color, that it might actually glow like a white because it's so hot? Well,
if it's visible light, we would expect to see it as a white light. And I think they specifically steer away from that because if you think about it, looking at other radio imagery, we've seen radio imagery in a variety of colors. So one of the standards might be and again, this is false color, just like Cosmic said, yeah.
Yep.
And one of the standards might be this orange. I've seen it before that's used, the different shades of orange. It's a pleasing color that can actually show the variations very nicely against black. So it is a very, again, it's an arbitrary color. It does not have anything to do with the energy. The intensity, though, does. So that's what that means. And I see that what's happening here. We got all right. Here, Ronald is asking Cosmic what he meant by false color images. Well, when you have something that's outside the visible spectrum, you can't see it in the visible spectrum. So how do you show it? Well, you show it by assigning a color to it, and then the pixel that point that has a certain value or intensity, you show by making it a brighter color or a different color. They could have shown this with a variation of colors, a gradient of different colors if they wanted to, where certain temperatures or certain energies were a certain color. And undoubtedly they will do that as well at some point. But this basically being a false color image, false color is how we show things that we can't see in a visible way. And so we assign false colors. On Mars, the rovers show a lot of the scenery in false color, and this, of course, led to a lot of conspiracies. But that was because the little blueberries, these little particles that were created in the presence of water, show up very well with this particular filter that's used to show them in a certain light. And so we use false color a lot. We've done false color with Sky Tour live stream so people could see how things are appearing, but not in real life. And then we show them the real life thing, and it's a little different, a little more convoluted. But when you look at it in the false color, you can see what's related just to oxygen, what's related to just sulfur, what's related to just hydrogen, and you show the different colors in different values. For instance, the Hubble Space Telescope, it has what's called a Hubble palette. It shows things very differently depending on what they are.
Yeah. You and I have talked about the Hubble palette before.
Yeah.
The problem I have with that is, well, hydrogen should be red, okay? And instead, I think on the Hubble palette, sulfur is red and hydrogen is blue, if I remember correctly. But there's another kind of false imaging, though, that I find interesting, is when the big boys at the professional observatories or at NASA, they combine images from different areas of the spectrum. Like they will show a visible light image, and then they will add X-ray image over that and infrared, and they will assign different colors like X-ray information from the Chandra Observatory. They might color blue or purple, and infrared stuff, they'll color green or red. And they will stack all those images together at the same image scale. And some of those are quite revealing about what is going on at wavelengths that we can see. There's pictures of the Sombrero Galaxy, M104, many others of M31 and Andromeda, stuff like that, and M82, which Mark has shown the other night, that show what's going on that we cannot see visually, yet it is still actually there, and it's actually happening when we look at it by combining all those visible and non-visible wavelengths of light into the same image.
That's right.
Why didn't they color it this way this time?
You'd have to ask them that.
Yeah, I mean, just the way they interpreted it.
Oh, okay.
Yeah, it could be. I mean, they could, like I said, each different energy level could have literally been a different color. And then you see this gradient. And well, in effect, it was, right? The least amount of energy was black, so to speak. The highest amount of energy was nearly white. And everything in between was shades of orange, different hues. And that's perfectly fine. That's exactly what you'd expect with the radio telescope.
Okay. Just a few more, I promise. Was something I jotted down, and maybe we already discussed this with the accretion disk. I wrote down black holes launch magnetic fields, magnetic field jets. They showed an image of two, areas with jets. I didn't catch the name of what they were showing us. And they were saying that there's probably, it might have been Sagittarius A, I'm not sure. But they said that another place they were looking that had possible black holes. And they were talking about the magnetic fields. So is that what's warping space?
That's what is constraining the jets. As I said earlier, black holes have three properties that we can find. One is mass, two is spin, three is charge. If you want to call charge electromagnetic, well, you're going to have an electromagnetic field from that charge.
Which means an electric field and a magnetic field.
And that is what is constraining, you might call focusing the jet into the well-delineated, stream that is shooting out the side of M87, for example.
Why is it just shooting at the side and not evenly around all of it?
It's shooting out the poles, the magnetic poles of the black hole, where the charge comes from, okay? It is shooting out from the poles, probably, the magnetic poles, and it's a huge amount of charge, and that in effect is focusing the beam that comprises the jets. We see the one jet at 2 o'clock when we look at M87. There is surely another jet coming out the other end, you might call it, of the black hole, whether it's rotational pole or the magnetic pole. Uh, they could be offset, just like the Earth's magnetic pole does not correspond to the geocentric pole. Uh, and the magnetic pole actually wanders quite a bit from year to year.
Hmm.
But that's what's creating and focusing those jets.
And we don't see it only in M87. We see it a lot of places.
Absolutely.
Other stars, we see it with plenty of other places, even in other black holes. They still also have these polar jets.
Yep.
Something else that they mentioned, someone during the question portion asked how large it was, and someone said a light day. Whose day? Is that an Earth day? Is that
The
Yes.
distance light travels in an Earth day, yes.
in an Earth day? So it was 24 hours, Earth hours across?
Right. Yeah, basically 24. Okay, no.
No.
Light travels 186,282 miles per second. Okay.
Okay.
Now you got to figure out the number of seconds in a day and then multiply that by a light day. And I don't think did he say one light day or did he say a little more than a light day? Do you remember, Daryl?
I thought he said about 1.5.
That's what I thought he said.
Well, I
Yeah.
wanted to figure out what a basic light day was anyway. Okay.
Well, if you remember when the New Horizons craft flew by Ultima Thule, how long did the radio transmission take to get from New Horizons to us? You're talking a matter of hours, part of a day. I forget the number. Call it 10 hours it took for the radio transmission to travel from New Horizons to Earth. Call it 10 hours. Well, you could do a little simple math and say that maybe the actual size of the black hole is 10 hours compared to 1.5 days, light days. Maybe it's about 2.5 times the size of Ultima Thule's orbit around the sun.
Yeah, and that would be the size. So
Yeah.
if you think about it, that's a large event horizon. That's a large radius. Let's put it that way. That's actually called a Schwarzschild radius.
Uh-huh.
And the Schwarzschild radius is something you can calculate. Now, knowing the size of the Schwarzschild radius, we can actually come up with a rough idea right now of what the mass of the black hole is, based on the Schwarzschild radius. And so we would just have to take, like, say, 1.5 light days, figure out how much that is in miles or any other convenient size you want in terms of the. I'm sorry, not miles. Take the Schwarzschild radius to get the Schwarzschild radius. We would just figure out how big it is in light days, and then convert that to miles or your favorite, unit, meters, kilometers, whatever you want. And then from there, we can actually figure out the mass of the object. Like, in other words, how many. It'll be a ridiculous amount of suns, but it would actually be. We could actually speak about it in terms of the mass of, say, our galaxy, and find out how many masses of our galaxy that would be, if that would be more appropriate. Because in astronomy, we find that astronomical numbers creep up really, really quickly. You quickly go from changing your units to something more usable.
Yeah.
Let me just go back to that Schwarzschild radius for a second.
Yeah.
Okay, if we know that the black hole is 1.5 light days across, well, then we can get the radius of what we see as the Schwarzschild radius. Okay, and then we can actually figure out the mass of the black hole, because the Schwarzschild radius is actually defined as 2 times g, the gravitational constant, times the mass of the black hole divided by the speed of light squared. What's that mean? Okay, it means we can solve for the mass of the black hole knowing that the radius r. And if we know that, we can all just do the solution, and basically it'll be the radius we get times the speed of light squared divided by 2 times the gravitational constant, and that will be the mass of the black hole. So we could actually do a armchair calculation to figure out kind of how big this galaxy is, or this black hole is in mass. So it'd be pretty interesting to see that,
Wow.
Yeah.
Armchair math.
Armchair mass, yeah.
Mhm. Okay, and this I think is going to be the last question, or just something for you to comment on. I saw at one point, Mark, you said during the stream, "Oh, here come the Sagittarius A questions or comments."
Yes, because I was
As
waiting
if,
for someone to ask.
why? What's so special about Sagittarius A? I heard a little bit about it, but tell me your thoughts on it. Why were you anticipating this to
Well,
come up?
Sagittarius A is the black hole that's in the center of our galaxy,
Ah.
and that's not 55 million light years away. That's under 50,000 light years away. It's about 30,000 light years away. So we should be able to see that a little bit better. In the radio spectrum, there's a lot of stuff between us and the Sagittarius A. So we're going to have more trouble seeing that than seeing M87 from a distance. M87 is a bigger galaxy, but it's an elliptical galaxy. It doesn't have dust. It doesn't have other stuff that obscures. It doesn't have that kind of problem. Our galaxy, though, we're in it, and it's trying to
forest for the trees.
Well, it's trying to measure a particular tree at some great distance through all the other trees you're looking at. You know, there's only a tiny little area through which we can actually see closer to the center of our galaxy, and only in the radio spectrum can we actually image Sagittarius A. So we have a chance, but it'll be kind of cool, and they're going to do it. You know, they're going to do it, but it's going to be very, very tricky to do. So
I got into it last night with some clown on Reddit. I don't know why I keep going back to that place.
And why you won't join Facebook.
Yeah. Okay, don't go there. Some guy had posted a very nice astrophoto he had taken in Hawaii of the Milky Way rising. And I made a comment, about a couple things you could see in the image. And some guy from Australia loudly proclaimed that the center of the galaxy was not in Sagittarius. He and I went around quite a bit about it, and I haven't been there yet today. He said something else, I know, because I got an email about it. If you want to see where the center of the galaxy in Sagittarius A, or Sagittarius A star, as it's sometimes called, if you can find the teapot in Sagittarius, okay, it's an asterism, not a constellation, but it's part of the constellation Sagittarius. If you look just a little to the right and maybe a little below the tip of the spout of the teapot, that is where the center of the galaxy is. Okay, you can't see it because, as Mark said, there's a lot of trees and gas and dust in the way and stars.
Don't say trees, Daryl, because people are
going to take I like that analogy.
Well, it was your analogy. You can't see the forest for the trees. Okay.
Yeah, I
like that.
Yeah,
I was with you, Daryl. I knew what you meant.
So was I.
That is where the center of our galaxy, and that is where the black hole at the center of the galaxy is just a little bit to the right and maybe a little bit below the tip of the spout of the teapot. If you just Google Sagittarius teapot, you should get a diagram showing it. It's a very pretty little asterism. It looks like a teapot with the handle on the left and the spout on the right. It's easily recognizable once you see it. You will never forget it. But all I'm trying to say is that's where the center of the galaxy is right off the tip of the spout of the teapot. Yeah. A little bit below M8 Lagoon Nebula.
Now I have that song stuck in my head. I wonder if there's a hidden meaning.
But the song The Lagoon Nebula?
No, I didn't know there was a Lagoon Nebula song.
Me either. I just made it up.
I meant I'm a little teapot song.
Oh.
Now I've got in my head. Darn you.
It's easy to see even from moderately light polluted skies. It is maybe a little smaller than the size of your hand at arm's length. Once you see it, you'll recognize it and you'll never forget it. Again, if you just Google Sagittarius teapot diagram, it'll show you a sky map that reveals the shape of the teapot. It's a popular asterism. Thousands of years ago, the Greeks saw a half man, half horse, a centaur, shooting a bow and arrow, because that's the kind of stuff they were into. This gets into that cultural angle again. Well, nowadays we don't see a centaur shooting a bow and arrow. We see a teapot, and it's cute. And there's lots of deep sky stuff, Messier objects, and other things all around it and inside it. So if you ever want to see where the black hole in the center of our galaxy is, just find the teapot and look a little bit to the right of the tip of the spout, and there you go.
Or go talk to that guy in Reddit who argues with Daryl about it.
Yeah.
No,
So
I
no-
remember you talking about the teapot asterism many times. I gotta remember these things. That's where. So, you guys are both saying that's where our center of galaxy is?
Uh-huh.
And your Reddit buddy was saying no? Okay.
Well, you know what? Here's the thing, okay? Keith mentioned it from P&K. Keith mentioned it at a previous time, actually in the previous stream. There is a there's a syndrome basically where people who have less ability to figure things out somehow perceive themselves as having more ability than anyone else, and so they say things that make no sense and say it with authority like it's exactly how it is. And I call them science-free people. I use that term, science-free. It's a little more gentle than giving them the clinical, psychological explanation, which is what Keith mentioned. But Keith is brutal with these folks. I can be sometimes, and because, but only with the people that choose to believe firmly in their theories without considering other evidence. I consider other evidence. If I have a solid theory I believe in, if there's other evidence, what kind of science guy would I be if I don't look at it? I mean, really, frankly. And so, and if Phil is still out there, he can tell us in the chat here what the name of that syndrome was that he mentioned, because I remember it. I'm trying to remember exactly what it was because it really made a lot of sense to me. It was hilarious too.
I guess flat earthers fall in this category also.
Well, clearly they do. Yeah.
Yeah.
I know what it is. It's called the Dunning-Kruger effect.
Oh,
Dunning,
sure.
Dunning-Kruger effect. Okay, and to state it properly, it's a cognitive bias where people with low ability have the illusory superiority that and mistakenly assess their cognitive ability as greater than it is. See, and that's the Dunning-Kruger effect, and that's what you mentioned. And I actually find that to be correct. I see that all the time, especially when we're talking about extraterrestrial life. It's a very touchy subject, and because we don't have a lot of evidence for any of it, really, then you think that you figure that some people will do that, and the Dunning-Kruger effect will be rampant, and it is. There's people out there that say they've been to Mars with Obama, okay, and they say it with a straight face, and you want to just laugh and then kick them in the pants. I mean, it's so ridiculous. Yes, Lorraine, Dunning-Kruger, just like that. And there's people say I've been part of a program going to Mars ever since I was a child. Why Mars? Why stop there? Why don't you just say Alpha Centauri or Proxima B? I mean, just come on, go for it. Make yourself, really, really important. And I think these are people that just, I think they're just people who just need to feel important. They need importance. Something happened to them in their childhood where they just didn't get enough attention or something. I don't know. But if you get the feeling that I do not believe them, then you get the right impression. I do not believe them. And I think that they may believe what they say. And that's sad because there's no reason for them to believe what they say. There's nothing they can show to prove any of what they say. So, but that's a whole nother thing. And, again, we'll probably talk about the human Martians on a future Sky Tour radio on kjraradio.com, I'm sure. We'll probably go down that path. We actually took on the flat earthers and kind of leveled them with inarguable, facts. For instance, a simple one, and I'll only give one. Orion up here has Betelgeuse at the top and Rigel at the bottom. Okay, Orion in the southern hemisphere has Betelgeuse at the bottom and Rigel at the top. Explain that. There you go. That's all I have to say. All right. So there you go. That totally deflates anything they can argue with, unless they want to start going down even further paths. Well, it's all an illusion. It's a hologram. Then they have to go down these other paths that say that the universe isn't real. So this is all part of the Dunning-Kruger effect. And I think that it's probably most rampant where we don't have a lot of scientific data for certain things. Okay. And that, of course, has to do with the concept of unidentified flying objects and extraterrestrial life. And there, I'm done. You may now proceed.
My feelings on such people, I think there are two sorts, two kinds, maybe more. One, people have always strived to make sense of the world around them, the larger world, the universe, whatever. And they think up these ideas themselves. And if it seems to be self consistent to them, that's what they go with. And they will not be moved from their position, okay? Even if it's not real, well, it more or less makes sense to them. The other kind, and I think this clown on Reddit last night, who was Australian, by the way, they know better and they do it anyway. They're doing it tongue in cheek. They're doing it just to be pains in the butt, and they think they're clever. There may be more kinds, but I think, the two general categories covers pretty much most people like that.
Mm-hmm. I agree.
Wow.
So, Amanda, what else you got?
That is it. Everything else I had, we already covered through other questions, so...
All right.
I just kind of... And I know I feel bad. I promised I would keep it quick. We've been almost on for a little over 2 hours.
I knew that would happen. And that's why...
know I had them written out. They were just going to be quick little talking points. I know it's a big topic, but...
They're not quick talking points because each talking point, even each question you had, required a lot of explanation and sparked a lot of discussion.
Yes.
It's all good.
Well, I mean, that is what I was after, sparking conversation.
Of course.
And you guys were wonderful. Thank you for humoring me, and I really appreciate your time. I'll let you guys both go, Mark's making faces. He was actually sharing camera to make sure that none of us fell asleep. We have the first part of the interview. It went well. We have the first part of the stream where the people from NASA and different companies were talking about the actual pictures of the black hole, what it meant for us, how we got it, everything. And then the second part was this discussion with Mark D'Antonio and Daryl Mason, two fine astronomers. I'm lucky enough to call them friends and have them join us for this wonderful, wonderful morning of question and answers. I hope you all took something away on this historic occasion. And enjoy the rest of your day. That's amazing.
Thanks again, everybody. Thank you, Amanda.
Thank you, Mark. Thank you, Daryl. I really appreciate it. Thank you for everyone that hung out and chat. I think it was a wonderful way to start the morning. I really appreciate your knowledge and your patience. And have a great day, everybody.
All right. We'll see you guys later.
Take care.
Well, there it is, folks. You heard it here first with Amanda Curran moderating Sky Tour Radio, this time a special edition on the Event Horizon Telescope. We'll see you again next week. And don't forget, keep looking up. Good night.